Question number 4, part A asks, what is the cobalt ion concentration in the solution if the absorbance of a sample of the solution is 0.74? So basically you're going to come up here to your graph, to that absorbance here around 0.74. You're going to come over to about here, and then you just come down. And again, I'm sure they gave you some leeway on this, but based on my terribly dotted line there, for answer A, I got zero, starts with a 0, so 0.013 molar would be the concentration. And I would imagine if you put 0.012 or put 0.014, they would give you credit for that as well. So probably anywhere between 0.012 and 0.014 they gave you credit for. Okay, and then part B, calculate the number of moles of cobalt in the 50 milliliters of solution. So we know that when you take the concentration, which is moles over liters, and you multiply by the volume, which is the 50 milliliters, so 0.050 liters, that will get us an answer that is just moles. So then multiplying those two numbers together, you get 6.5 times 10 to the minus 4th moles. This answer right here is a 1-point response. This answer right here is a 1-point response. So we've got 1 and 2 so far with A and B. Then part C, calculate the mass percent of cobalt in 0.630 gram sample of that ore. So that means that we need to get the mass of the cobalt over the mass of the whole thing. So we're going to put 0.630 grams of the ore on the bottom. So really, we just need the mass of the cobalt. And we know that, again, we've got the moles of the cobalt in part B. So the first thing we're going to do is we're going to take 6.5 times 10 to the minus 4th moles. And then we're going to use the molar mass. 1 mole of cobalt has a mass of 58.93 grams. And I get a mass of 3.83 times 10 to the minus 2nd, or just 0.0383 grams. And if you got that answer, that was worth a point. And that is the number that we put on the top. That is the grams of the cobalt. We put that over the 0.630 grams of the whole ore. And now we simply divide those two numbers and we multiply it by 100 to get a percent. And I got 6.08%. And you also got 1 point for that response as well. So here's point number 3. Here is point number 4. So give yourself a score out of 4. Okay, question number 5. First of all, part A, predict the sign of the entropy change for the reaction. Justify your answer. You're going from solid and aqueous to aqueous liquid, and more importantly, gas. So absolutely the sign of the entropy change is positive. Justify your answer because you are producing a gas which is much more disordered than a solid and an aqueous in the reactant side. Okay, and that, I believe, yes, it's just a 1-point response there. So we've got 1 point for part A so far. Part B, calculate the enthalpy change for the reaction using enthalpies of formation. So here is where we use the enthalpy of formation of the products minus the enthalpy of formation of the reactants. And remember, things that are in their elemental form. Remember, the enthalpy of formation is forming something from its elements. So if something is in its elemental form, it has an enthalpy of formation of 0. So the enthalpy change for the reaction is going to be the enthalpy of formation of our products here. So we've got silver nitrate, and we've got 3 of them, and there's silver nitrate. So we're going to take 3 times negative 101. And then we've got 1 nitrogen monoxide. So we're going to add up all the products. So there's only 1 of them, so that's 90. And then we've got 2 waters in the liquid form, so 2 times negative 286. and that is the sum of the enthalpies of formation of the product. So it's the enthalpy of formation of the products minus the enthalpy of formation of the reactants. Silver's in its elemental form, so it does not have an enthalpy of formation. However, HNO3 does, and there's 4 of them, so that's minus 4 times negative 207. And then you simply add and subtract and do what you need to do there. The enthalpy change is a positive 43 kilojoules per mole. Units not required there. Okay, and that also is simply a 1-point response if you got the answer of 43. Okay, and that's part B. Part C. Based on your answers in parts A and B, is the reaction more likely to be thermodynamic favor at 25 or 95? So low temperature, high temperature. So in this case, in part A, we got a positive delta S, and in part B, we got a positive delta H. So we know that in this case, they're both positive. So remember, when the signs of delta H and delta S are opposite each other, then it's either always thermodynamically favorable or never thermodynamically favorable. When the signs are the same, when they're both positive, like in this question, or if they're both negative, then it depends on the temperature. And remember that when we use delta G equals delta H minus T delta S, that at low temperatures, enthalpy has more of the driving force, plays a bigger role in determining the value of delta G. At a high temperature, the negative T delta S plays the bigger role. So the question is, which of these is more likely to make it thermodynamically favorable? So we're trying to get a negative delta G. Well, at a low temperature, what plays the bigger role? The delta H component. Well, delta H is positive. Delta H does not make delta G negative. Delta H would make delta G positive. So at the low temperature, delta H does not help us. It hurts us from it being thermodynamically favorable. As the temperature goes up to, say, 95 degrees, now again, this part right here is now playing the bigger role, because when delta S is positive, this whole thing here with that negative sign there is negative. So therefore, as the temperature goes up, this part starts to play the bigger role, and as it plays the bigger role, eventually it's going to switch from this playing the more important part to this playing the more important part, and delta G will be negative. Okay, so is it more likely to be thermodynamically favorable at the low or the high temperature? Absolutely the high temperature, 95 degrees Celsius. And why? Because the positive delta S makes negative T delta S larger, and delta G negative at higher temps. Okay, just a 1-point response. So if you have the right answer and then you have something about the positive delta S or the positive delta H, something along those lines, they're going to award you the point, and that is just a 1-point response there as well. Okay, and then part D, the student runs the reaction using a 3 to 4 mole ratio of silver and nitric acid. So you can see a 3 to 4 ratio. Basically, they're saying there's no limiting reactant. They're both going to run out at the same time. So there's no reactant left over. That's really what they're trying to get across to you there. So then it says, suggest a method the student can use to isolate the silver nitrate. So first of all, well, what do you have in your, this is a 3 to 4 ratio, that's all gone. There's no excess reactant left over. So what did you make in this reaction? Well, you made nitrogen monoxide gas. That's going to go up into the air. So that's already gone. So really you've got some silver nitrate dissolved in water. Okay, if it's dissolved in water and you're trying to isolate the silver nitrate, how do you get rid of the water? Well, how do you always get rid of water? Is you boil it off. So you heat it up, you drive the water off using evaporation, but a method the student can use to isolate the AgNO3, I simply wrote boil the water. Okay, and that's going to drive the water off, and you're going to be left. How do you isolate salt water? If you just want the salt, you have to get rid of the water. Okay, just a 1-point response there as well. So that was, there's 4 parts, each of them worth 1 point. So that's 4 points there for question number 5. Question number 6. calculate the amount of heat energy needed to raise the temperature by 180 degrees. So that's our temperature change. There's our specific heat. And up here they give us the mass. Okay, so we know that Q equals mc delta T. In this case, they gave us the mass of the beaker, not the moles, because remember, sometimes they try to trick you with that specific heat and they put joules over moles Celsius or moles Kelvin, and then you have to use moles instead of grams. So they didn't do that in this case. So the mass is 1,650 grams. The specific heat is 0.810 joules over grams degrees Celsius, and the temperature change is 180 degrees Celsius. Remember, in this case, the temperature change, it doesn't matter if it's Celsius or Kelvin. In both cases, the temperature change is going to be the same. So the grams cancel, the Celsius cancel. We're just left with joules, and Q is equal to 2.41 times 10 to the 5th joules. Or you certainly could put that into kilojoules as well. It'd be 241 kilojoules. Either of those answers would have been accepted, and that is just a 1-point response for either having joules or kilojoules there. Okay, part B, calculate the number of moles of butane that was used in the experiment. Well, the mass of the burner before combustion was 225.26. The mass of the butane after the combustion was 2.18.20. So why did the mass change? Well, because you used some of the butane. Well, how much butane did you use? Well, you used 225.26 minus, not divided by, 225.26 minus 218.20 equals 7.06 grams of butane. Okay? And then at some point earlier here, they tell you that the chemical formula of butane is C4H10. So we get the molar mass of that, which is 58 grams per mole. And we get 0.122 moles of C4H10. And that's it. They're asking for the number of moles. We've got the number of moles. That's a 1-point response. Okay, part C, using the balanced equation, determine the amount of energy produced by the combustion of butane in the experiment. So we know that 2,659 kilojoules get released for every 1 mole, so every one time that whole reaction happens. Okay, well, we didn't use that much. We used 0.122 moles of C4H10. So we're going to start with 0.122 moles of C4H10. And then we're going to use the balanced equation to say that 1 mole of C4H10 reacts every one time that whole reaction happens, which is 1 mole of the reaction. Now, in this case, obviously, if you skip this step, they don't care because it is a 1-to-1 ratio. But of course, if there's a 2 right here, well, then that changes everything, because then you would have to have a 2 right here for moles of C4H10. Obviously, in the real reaction, you don't. But certainly in this case, if it were any number other than 1, and that's why that mole of reaction step right here is really, really important, because if it was involving oxygen or water or CO2, then absolutely you're not putting a 1 right here. You're putting whatever that coefficient is in that balanced equation, because now the rest of it's pretty easy. Now we just use the enthalpy, 1 mole of the reaction, 2,659 kilojoules, and we get our answer, which is 324 kilojoules. Okay, and that was just a 1-point response. Basically, if you have the right answer, they're going to give you credit for it. Okay, and then part D, the student claims that some of the heat energy produced by the combustion of butane was lost to the air surrounding the system. Do your answers to part A and C support the student's claim? Well, in part A, we found that you need 241 kilojoules to heat up that sand all the way. In part C, we found that the reaction actually releases 324 kilojoules of heat. So did some of that heat get lost to the surroundings, the air, to whatever? And certainly it did. And how do we know that? Well, because it actually produced 324 kilojoules of heat, but only 241 kilojoules of heat were absorbed by that sand. And so, yes, the students, do your answers to parts A and C support the student's claim? Absolutely, yes, they do. And how would you explain that? Because only 241 kilojoules were needed, yet 324 kilojoules were produced. Okay, and that's also a 1 point response. Again, this question did have 4 parts, each of them worth 1 point each. So give yourself a score out of 4 on that one. And then our last one, question number 7. Looks like we've got 3 different solutions here. So in solution X, so let's go through each of these first before we start to answer the question. So solution X, 100 milliliters of 0.10 molar sodium hydroxide. So we know that's a strong base. 100 milliliters of 0.10 molar HBr. We know that's a strong acid. We know that the volumes are the same. The concentrations are the same. And so if you put the two of those together, what happens when you put a strong acid and a strong base together? You make water. And basically, if this were a titration, right now you're exactly at the equivalence point where all of the acid is equal to the amount of the base. And so right now you have a pH of, again, exactly 7. Any strong acid, strong base titration is going to have a pH of 7 right at the equivalence point. Again, this is not necessarily a titration, but if it were, and even if it's not, you pour those two together, you're going to have a pH of 7. Because again, what are you going to have floating around in there? You're going to have water, and you're going to have NaBr, which is going to be soluble. So you're really going to have Na plus and Br minus. Okay, solution Y, again, you've got that strong acid HBr, and you've got some NaBr. So NaBr is obviously going to break apart again into Na plus and Br minus. So really what you've got is you've got a really, really strong acid, and you're going to have some of its conjugate base, which is very weak in it as well. So really, this is just a strong acid solution, okay, that has some Na plus and Br minus in it. And then solution Z, you've got a weak acid mixed with, some of its conjugate base. Oh, a weak acid with its conjugate base. Absolutely. That is, again, an acidic buffer solution. And again, even if you didn't remember that HBr was a strong acid and acetic acid was weak, they tell you that right here. Okay, when you have a very, very large Ka, that's telling you that's a strong acid that completely dissociates, whereas that with such a low Ka tells you that's a weak acid. However, you should have known that already. You should know what the strong acids are. So part A says, using the information above, write the letters of the solutions in the boxes below to rank the solutions in order of increasing pH. So we're going to start with the lowest pH and go up to the highest pH. So solutions Y and Z are both acid solutions. So we know they're going to have lower pHs than solution X. So right away, solution X is going to be our last one. Okay? So now it's just which one is more acidic, which one produces more hydrogen ions is really what you should be thinking here. And certainly a strong acid with the same volume and concentration as a weak acid is going to produce way more hydrogen ions than a weak acid buffer solution is. So therefore the lowest pH is going to be solution Y. And then obviously the one in the middle that's still acidic, that's a buffer solution, is Z. Okay, and then explain your reasoning for the ranking. Again, I would just quickly go through it. Solution Y is a strong acid solution. Z is a weak acid buffer. And X is a neutral solution. Okay, and they did award you 2 points for this. 1 point for having that answer, the order correct, Y, Z, X, and then another point for your explanation here. Okay, and then obviously, so that's worth 2 points, and then part B and C are each both going to be worth 1 point. Okay, part B, does the pH of solution Y, so solution Y again is our strong acid solution. Does the pH of the solution increase, decrease, or remain the same when 100 milliliters of water is added? So when it's a weak acid solution and you add some water to it, that's like increasing the volume of a gas. You're increasing the volume. In an equilibrium system, it's going to shift to the side with more aqueous particles. Okay, however, HBr is a strong acid. It is not an equilibrium system. And so by adding some water to it, all that you're doing is you're diluting that acid. And by diluting that acid, what are you doing to the hydrogen ion concentration? Because remember, the pH is 100% based on the hydrogen ion concentration. So if you have X number of hydrogen ions in there and then you add some more water, well, now that's more dilute. So the concentration of the hydrogen ion has gone down. And as the concentration of the hydrogen ion goes down, we know that's directly related to the pH. The pH absolutely is going to go up. Okay, and so does the pH of the solution increase, decrease, or remain the same? Absolutely, it is going to increase. Okay, and then to justify, you're going to say because the hydrogen ion concentration decreases as water is added. Okay, and then part C, and that obviously just a 1 point response to get us up to 3 points there. And then part C, a student adds some sodium hydroxide to Y, they add some sodium hydroxide to Z. The volume doesn't change, and it says the pH of Y changes much more than solution Z does. Explain this observation. Well, again, in solution Y, we've got a strong acid. You have a whole bunch of hydrogen ions floating around in there. So when you add some strong base to it, what does that base do? The OH minus ions immediately react with the hydrogen ions to produce water. And then just like in question B, that when you remove hydrogen ions from the solution, what does the pH do? The pH is absolutely going to go up. Okay? So in solution Y, the OH minus reacts with the H plus to produce water, which raises the pH. Okay, however, in solution Z, we already identified this as a weak acid with its conjugate base. We already identified that as a buffer solution. Okay, and so we're going to say that Z is a buffer solution. And again, you don't need to say really much more than that, but let's understand why. So when you add hydroxide to a buffer solution, remember the buffer solution contains the acid and in this case the conjugate base. So in this case, this base that you added is going to react with the acid component of that buffer solution to produce some water and some C2, more of the conjugate base. And therefore, what happens to the hydroxide that you added? It gets used up. And so what does the pH do? It doesn't change very much. So the Y solution changes much more than the pH of solution Z. Okay, and so all that hydroxide's gone. You've used up some of the acid. You have some more of the conjugate base now. But again, really, it's just identifying that as a buffer solution. This is just for your own knowledge as to why. Okay, so overall, 4 points there for that last question. So overall for this test, we're going to take the multiple choice. So you have a score out of 50 on the multiple choice. Let's see that score. You're going to take your free response out of 46, whatever that number is, times by 1.0869. And then you're going to get a final score out of 50. So get that number there. And then take your multiple choice, take your free response, add them together, get a score out of 100. And on this test, the scoring went like this, a little bit lower than normal. Anything from 75 to 100 was a 5. The 4 went all the way down to 60, so 60 to 74 was a 4. The 3 went from 44 to 59 was the 3. A 2 went all the way down to 30 to 43, and then anything from 29 down was a 1. So give yourself a score, please. Send that to me, and you're done with the 2018 test.